we have discussed many classifications of the signals. So signals, they can be continuous, they can be discrete time. Okay, and so that's a very broad classification of signals that we are going to deal in the in the context of signal and systems and analysis. Well, the signals we also talked of, they can be either they can have a finite energy and zero average power, or they can have finite average power but infinite energy. So signals can be either energy signals, they can be power signals, or they can be neither. Okay. So further classification that exists in the context of signal systems and analysis is we can have periodic signals or aperiodic signals. Okay. So a periodic signal is one for which this relationship, the given equation, holds. What it says is that if you transform the signal, if you delay or advance the signal, a time-dependent signal, by capital T, a smallest, let's say, positive or negative, doesn't matter, but a small real quantity, let's call it capital T, if it exists, and if it is delayed by that amount, capital T, either it is shifted towards left or towards right. The result that the transformation that results after you shift the signal by amount capital T in time, gives you back your original signal xt. So if this relationship holds for all t, then xt is periodic. Okay, so a periodic continuous time signal xt has a property that there is always a positive value of t for which xt is equal to xt plus capital T, for which the relationship basically holds. Okay, I mean, for example, look at this figure which is showing you a continuous time periodic signal. Why it is periodic signal? Because if I shift the signal by, again, some real quantity, some positive real quantity capital T, which happens in the period. Okay, if I delay this by capital T, then this part of the signal is going to be shifted. All the points, all the samples, all the points, all the discrete points that are constituting this that are constituted into xt in this part of the signal are going to be shifted by the amount capital T towards right. Okay, then what happens to this copy of the signal? This part of the signal is going to shift itself again towards right by the same amount. Okay, and then this part is again going to shift by the same amount capital T. Similarly, in the place of this part of the signal, this is not going to be vacant. Okay, this is not going to be empty. This part of the signal is going to come in the place. So this will be centered around 0 now. So this is going to shift towards right, and this is again going to shift towards right. So at the end, what we are going to see, and this trend continues. Okay, both on the on either side of the time axis, this trend continues. So if you're going to delay the signal by an amount capital T, okay, if it exists and if the signal is periodic, then under this transformation you see that capital T happens to be the period of the signal xt. Why? Because an equality holds under this transformation that if you're going to delay the signal by a certain positive real quantity capital T, if the time axis is shifted, then it turns out that under this transformation and by introducing shift in time, there's no difference. Okay, xt minus t is still equal to xt. Okay, you get back your original signal. So this is periodic. Okay, and it doesn't matter if you shift this, if you delay this in time. I mean, the shift could be towards right on the time axis, or it could be advancement toward the shift could be left. Okay, it doesn't matter if I introduce plus over here. You see what happens if I introduce plus is that this part is going to shift towards left. Okay, then this part is again going to take the center origin position. Okay, and the center origin position part of the signal is going to shift towards minus t. Then this part which is centered at minus t is going to shift at minus 2t, and this trend continues. Okay, this trend continues on the other side. So it doesn't matter. T has to be a positive and a real, unless there exists a positive real quantity, smallest positive real quantity capital T, by which if the signal is advanced or delayed in time, you get back your original signal xt back. So that positive, that smallest positive t is your is your period. Okay, so this t corresponds to the period of the signal. Okay, so we call this period. Just call this actually precisely the fundamental period. Why? Because you can also go on shifting this by, let's say, integral multiple of period. So it can be shifted by 2t or 3t. What happens if I shift xt by 2t? You see, the equality still holds. I mean, this can be shifted by 2t. What happens in this case is you still get back your original signal. You see, it still looks like the same. So what happened is, under this transformation, is that this x of t is going to shift. Either it will be advanced, or it's going to delay. If this is the negative sign over here between t and 2t, so negative operator, then you're going to shift. There will be a delay in time. If there's a positive operator over here in between, then there will be an advancement in time. So what happens is that this part of the signal is not going to shift itself, and it's not going to center itself next at capital T. It's going to center itself at twice T. Okay, basically this is going to shift over here. All right, and this 2T is going to shift at 4T. Right, so this trend continues, and again, I mean, this minus T is going to come at there will be a jump of 2T over here, so this is going to take this place. Okay, this minus 2T is going to come at 0. Okay, and similarly the advancement operations are also the same. The shifting will be towards left with the step of twice t. Okay, so under these transformations, you see, again, under these transformations, you're getting back your original signal. Okay, so from the above equation, we can readily deduce that if xt is periodic, and that is a certain real positive quantity capital T exists for which the equality holds, for which this equality holds. If xt is periodic with period t, then xt should be equal to xt plus mt, where m is an integer, right? So for all t, for any integer m, thus xt is also periodic with period 2t, 3t, 4t. So the fundamental period happens to be the smallest period, and in this case, the smallest period is capital T. So capital T, if you refer to capital T as t naught, okay, it's the same quantity. So capital T is we are referring to t naught as the fundamental period. So this is the smallest positive value of t for which the above equation is holding. So you cannot have this equality for, let's say, if you consider this this figure, the continuous time periodic signal that is being shown in this figure, and this equality doesn't hold for let's say xt. You cannot say that xt is equal to x t plus t by 2. You cannot have a fraction of t. No, you can't do that. If you do that, well, you're going to vacate this place. This is not possible. This is not equal to xt. So you cannot have this equal to xt by 2 or xt by 3. So what happens is over here is that, for example, if this is t by 2 and this is minus t by 2, then you see the part of the signal that is centered at 0 is going to shift itself at t by 2. Okay, and you will have a vacant position at you will have nothing that's being you will have nothing centered at t equal to 0. So that's not xt. That's something else, right? So that's not xt. So t by 2 is not the period. So smallest real quantity for which this equality holds is capital T, and that's the period. That's true for all t, right? I mean, if you are going to do that, things will become something like this. Okay, and then again, this is going to shift over here. So this is not xt. This red one is it's not equal to your xt, right? So the smallest positive quantity by which you can reproduce under the transformation of time shift and the original signal back xt is capital T, and this is the period, and we said that this is the fundamental period t naught. Okay, so periodic signal has a property that it is unchanged by the time shift t. So that's the philosophy. That's it. I mean, the periodic signal is it remains unchanged. It does not undergoes any change if the transformation of time shift is made. So in this case, we can say that xt is periodic, period t. That's it. Okay. So what about the constant signal? Okay, I mean, constant is not a signal philosophically, right? Because constant is not conveying any information. If you recall, in the very first lecture, we said that signal has to contain some information into the fluctuations which are evolving with respect to time, or the independent variable which is in consideration. So if there is no fluctuation, if there is signal, if there is no information contained in the signal, well, that's your constant phenomena. Constant is constant. I mean, with respect to time, it's not changing, it's not conveying any information. There's no pattern of fluctuations, there's no information. So what about a constant? Well, for constant, this definition of periodicity for fundamental period, the definition of fundamental period works except if xt is a constant. So you cannot have a fundamental period. Why? Because for a constant signal, philosophically, the time period is going to be indefinite, right? It's going to be infinity, because, for example, if you have a constant, if you have a DC signal and you plug this into a spectrum analyzer, you're going to see a peak having certain strength proportional to the amplitude of the constant signal at frequency equal to 0, right? So if frequency is equal to 0, that means the time period is indefinite. In other words, just as we consider the definition of periodic signals, in this case, the fundamental period is undefined, and since xt is periodic, for any choice of t, there is no smallest positive value, okay? I mean, the t naught is undefined. I mean, it goes to infinity philosophically, and there is no smallest fundamental period that is defining the period of a constant, okay? A constant is a constant, so the frequency is 0, the fundamental frequency is 0, the fundamental time period approaches to infinity. So you don't have, there is no smallest positive value of t. So under these conditions, constants are not periodic, okay? I mean, I would say they're not even signals, right? So constant phenomena has nothing to do with periodicity, right? So a signal xt that is not periodic, we're going to refer to as an aperiodic signal, okay? So an aperiodic signal is one for which the equality does not hold, and you cannot have smallest positive quantity capital T, by which if you shift the signal in time, you delay it or you advance the signal. Under this transformation, if you don't get back the original signal, the signal is aperiodic. If you cannot find the smallest positive capital T, the signal is still aperiodic, okay? All right, now a similar analogy holds for the discrete time signals. That is, periodic signals are defined analogously in discrete time. Specifically, a discrete time signal xn is periodic with period n, where n is a positive integer. So here's the difference. You see, previously we said that t is any positive real quantity, okay? We said that there's a positive value of t for which this equation holds, okay? So t could be anything. T could be 5.13 seconds, it could be 10.9 seconds, it could be 7.23, it could be pi, or whatever it is. It could be any irrational number, it could be any positive quantity. But for discrete time case, here's the distinction. The shape of the equation looks very similar, but the constraint is that this capital N has to be integer. It must belong to positive integers only. Okay, why? Because small n is an integer, and to an integer you cannot add a fraction. You have to add an integer. So the constraint is that n must belong to positive integers. Okay, it doesn't make sense that n could be negative while being an integer. Okay, you cannot have a negative period. It doesn't make any sense. So it has to be a positive quantity. N has to be a positive quantity, number one. Number two, it has to belong to a set of integers, right? So that's the difference between periodic sequences and periodic signals. So n has to be positive integer. And if it is unchanged by this transformation, by the time shift of n, then if this equation holds, we say that xn, the discrete time signal or the sequence, is periodic. So if the above equation holds, xn is also periodic with period 2n, 3n, and the fundamental period being n naught, which is the smallest positive value under which the above transformation holds valid, and you get back the original sequence. Okay, so n has to be integer. That's the only difference for all n. So an example of a discrete time, periodic discrete time sequence, you can see by inspection, looking at the samples of x of n, that this sequence is going to repeat itself after capital N equal to 3. So after the 3 samples, so this is, for example, 0, this is 0, this is 1, this is 2. If you are going to include the 0 sample, you're going to count the 0 sample as well. And then there are 3 samples after which the sequence x of n is repeating itself. So well, this is equal to x of n plus 3, right? So 3 happens to be my fundamental period. This is capital N, right? This is capital N. Well, it also is valid for, you see, integral multiples of capital N. I mean, this equation is also valid for N plus 6, right? But the smallest period is to be counted as the fundamental period. So discrete time periodic signal has a fundamental period N naught equal to 3 N naught. This is N naught, okay? And this is basically twice N. This 6 is twice N naught. Okay. So the fundamental period has to be the smallest N naught, which is integer in case of discrete time sequence. And if it exists, then by shifting this by the same amount N naught, the sequence should remain unchanged. Okay, so this is an example of discrete time periodic signal. The fundamental period N naught equal to 3 is shown in the figure below. So this is very easy to classify the signal as periodic just by inspection. Let's consider a more involved example. So in this example, you see xt is given as cosine t if t is less than 0. It is sine t if t is greater than 0. So this depiction is showing you a sinusoidal waveform. So for t greater than 0, t greater than or equal to 0, you have a sinusoidal waveform. For t less than 0, this is a cosine function. Okay, this is a cosine function. So you see, there's a as the signal is defined, there's a discontinuity that occurs at t equal to 0, and this discontinuity is not occurring anywhere else. I mean, you see, you know that a sinusoidal signal or a cosine signal is always periodic. So, for example, if you partition the signal for t greater than 0 and for t so for t greater than or equal to 0 and for t less than 0, and in these partitions, the signal is periodic, right? Sine and cosine functions are periodic. So from trigonometric identity, we know that cosine t plus 2 pi is cosine t. Similarly, sine t plus 2 pi is sine t. Thus, considering t greater than 0 and t less than 0 separately, we see that xt does repeat itself over every interval of length 2 pi. However, this follows from the trigonometric identity, right? I mean, you can see this over 2 pi, 4 pi, okay, 2 pi being the fundamental. This the trend continues, the trend repeats. Okay, the sinusoidal functions are repeating it themselves. But if you consider xt as a complete signal, so you see, as illustrated in figure below, xt has a discontinuity at the time origin, and this does not reoccur at any other time. The thing is, this discontinuity is not occurring at any other time. Now, for continuous time signal, the philosophy is that you must find for all t. So if you recall, probably we have not emphasized on this fact that, there has to be a small positive real quantity capital T for which you get back xt and this transformation, but this has to be valid for all t, right? But over here, for all t, this point is not reoccurring, right? So xt is not periodic. So since every feature in the shape of the periodic signal must reoccur periodically, so we conclude that the signal xt is not periodic. Xt is not periodic. Okay, so this definition is not going to hold for all t. If you partition the signal for t greater than or equal to 0, t less than 0, well, fine, we can still work this out. I mean, but as a complete signal for all t, this is the definition, if you recall, for the continuous time signal periodicity. This has to be valid for all. This has to be valid for all t. So all the points in time of the signal, they have to repeat. Okay, but we cannot have the repetition of, if we cannot have the repetition of one point, which, for example, over here, the jump discontinuity cannot be reproduced at one point, then the signal is aperiodic. If any point is not repeating, if any one point is not repeating, as in the case over here, signal is aperiodic. The signal is aperiodic. Okay. All right, now one distinguishing feature that I wish to talk about here is that while there is a statement that while all continuous time sinusoidal signals are periodic, the same is not true for discrete time sinusoids. I mean, okay, we know that cosine t or sine t are always periodic. Let me have this alpha t, okay, where alpha is a positive quantity, and let's have a phi. Phase doesn't matter as much, but this is always periodic. So continuous time sinusoids are always periodic. Why? Because you can always work out a small positive quantity capital T under which the periodicity will hold. But this does not hold true for the signals which are discrete. Okay, so discrete time sinusoids are not always periodic. Okay, I mean, for example, for this signal, if you try to work out the fundamental period, you can always go back to the definition and you can plug this like T plus capital T plus phi and see if you can if this equality holds between these two expressions. Okay, and to have this equality true, the constraint is that alpha t should be an integral multiple of 2 pi. Okay, it should be 2 pi k, right? That means your fundamental period capital T is 2 pi by alpha. Okay, 2 pi by alpha. This is your T naught. This is the fundamental. I'm not writing K because K is going to make since we are looking for the smallest positive real quantity T, and that happens to be the fundamental period. But in general, any quantity which is of the form 2 pi, which is an integral multiple of 2 pi by alpha, is the period of the signal, right? So all the discrete time sinusoids, sine and cosine doesn't matter. You can always work out the period like this, and your fundamental period happens to be the smallest time period by which, if you shift the signal, the sinusoidal signal, it's going to give you back the original sinusoid, so it's periodic. So what happens in discrete time sinusoid? For example, what if I have a discrete time sinusoid of the form cosine phi n, cosine phi n? So is this periodic? Not unconditionally, you see. Why? Because if I'm going to plug this into the definition of periodicity to check if it is periodic, if I can get back, if I can reduce smallest positive integer for which this equality holds, it should be of the form 5 n plus capital N. Okay, then this would imply, if it is periodic, then 5n should be an integral multiple of 2 pi k, right? Is this possible? I mean, does this equality holds? I mean, there's a problem with this equality. The problem is that n is an integer, right? 5 is an integer. So an integer into an integer is some other integer. But on the left hand side, I don't have an integer. Well, k is integer, 2 is integer, fine. But pi is not an integer. It's a fraction. So this is not the case. Okay, so I'm not going to have n as an integer. So the periodicity does not hold. The only condition is that the angular frequency of a discrete time sinusoid, unless it is an integral multiple of pi, you cannot say that the discrete time sinusoid is periodic. So let's try cosine of 5 pi by n. So I'm going to make the angular frequency a multiple of pi over here. So 5 pi by n, let's say. Okay, and if I'm going to, if I need to find the smallest positive integer for which the periodicity is going to hold, I can do that now. So you see, the definition, this is 5 pi n plus capital N. Then, well, you see, then 5 pi by n, 5 pi capital N has to be an integral multiple of 2 pi, and in this case you can find the period capital N, right? I mean, this pi is going to go out, and the period capital N that you're going to find out is 2 by 5 k, right? Again, looking at this expression, you see why k is important, because this is going to be valid for k equal to 5 only. The fundamental period, you can work out the fundamental period for k equal to 5. So the period, fundamental period, and not for k equal to 5 is 2, right? So you can find the integer, right? This is the integer that we require, and that's the condition, because if you are considering a discrete time sinusoid, okay, in which x is a sinusoidal function, Then, as you see in the definition of for periodicity, if this equation holds, then n has to be an integer. To an integer, you can only add an integer. You cannot add a fraction. You cannot go ahead and add a fraction. So you see, if this is the this is the case, then what happens? So if I'm going to replace this n by 2, well, this is equal to cosine. This becomes equal to cosine 5 pi n. This becomes equal to cosine 5 pi n plus 10 pi. And what is this 10 pi? You see, this is precisely an integral multiple of 2 pi. So this expression is the same as cosine of 5 pi by n, which is my original sinusoidal sequence, discrete time sequence. So to have discrete time sinusoids to be classified as periodic, an additional condition applies on the angular frequency that this should be an integral multiple of pi. Unless it is not an integral multiple of pi, like in this case over here, it's not periodic. Okay. So for discrete time sinusoids, or for discrete time in general, for discrete time sequences, capital N has to be strictly an integer. Okay, because to an integer you can only add an integer. You cannot add a fraction to it, which you can do otherwise for a continuous time signal, because t is going to exist for a continuum values. Okay, it can take the values from a continuum. T could be 0.1, it could be 11.3, it could be anything, right? So likewise, capital T is also some real quantity. So for continuous time sinusoids, it's always periodic, and for general continuous time signals, which are not sinusoids, T could be any real quantity. It could be any it could be any fraction. It could be an irrational number. It could be decimals, whatever. Okay, right. So, but for discrete time sequences, it has to be an integer only. Okay, so that's the distinction.